So today we move on to see another type of reaction and understand its mechanism, that is the nucleophilic substitution. Because this type of reaction, the substitution reaction, is quite common in the alkanes. And to remind us what is a substitution, is the reactant molecules exchange atoms or groups of atoms to produce two new product molecules. And in general terms, this is how it can be understood. Two reactants A, B, and C, D, if they react together, exchange parts, and the result are two new products. They have exchanged molecules, or atoms or groups of atoms. And some examples that involve some saturated hydrocarbons or heterocarbons, and saturated organic compounds, like this bromoethane here, reacting with sodium hydroxide or sodium bromide, or an alcohol here, ethanol, reacting with hydrogen bromide, and so on. I mean, these are types of substitution reactions, and we're going to see now the mechanism of some of them, some of the substitution reactions. In fact, I would like us to look at three aspects of substitution reactions. One where we have a reactant reacting with a negative nucleophile, like hydroxide or cyanide. Then another case where we have some organic saturated compound reacting with a neutral nucleophile, and a prominent example is when they react with ammonia, which I want us to do quite well because it might be a little bit complex. And then the mechanism of when we have, like in this last example where ethane reacts with chlorine gas. And because here we have a special case where we have the formation of free radicals, and I would like us to discuss this as a third case of substitution reaction. Now let's see how far we can go, and let us start with the first aspect first, where we have a reaction with that involves a negative nucleophile which contains like hydroxide or cyanide. This is the first reactions of this is an example of a reaction where we have this hydroxide involved here, like the sodium hydroxide, for example. So let us see what happens now. How does the hydroxide replaces the bromine atom from the saturated bromohalide. Okay, so there we have again the same reaction to remind us. This is bromoethane. And now let us write the bromoethane in this form where we can see all the bonds involved clearly. So these are hydrogens here. And this will react, well, we're interested in the hydroxide. The hydroxide, which is a negative ion, and we need to show that it has a pair of lone electrons, and we need to show this pair of electrons on the hydroxide. I mean, if in case that they ask us to explain the mechanism of such a reaction. All right, so all right, now, so now this bromoethane, it's a polar molecule. Why? Because because of the difference in electronegativities between the bromine atom and the carbon atom to which it is connected. So this will have a partial negative charge, and this carbon here will have a partial positive charge, and we also need to show this partial charge, these deltas here, in other words. So you see, this shows that this is a polar molecule. This is the more negative part. This is the more positive part. And this is our nucleophilic item, which means it is attracted to electron poor centers like this carbon here, because it is considered an electron poor. It has a partial positive charge. So what happens here now is that this pair of electrons will form a covalent bond here with this carbon. And what's happening now, we are going to, at the same time, this pair of electrons that is represented by this bond here, this pair of electrons will move to this bromine atom. And the result will be that, let's write it again down here. This carbon stays as it is. Now this carbon joins to the hydroxide. This hydrogen stay there. That will be the hydroxide here, new one. And what we have left now is this bromine atom that took both the electrons of this pair of electrons, and we have to show that these two pairs again. And this is, of course, negative now. And we have now that the hydroxide, which was the nucleophile in this case, has substituted the bromine atom, which is now has become a bromine ion, in other words, a bromide, as it has gained both of these electrons here from this bond. Okay, and remember, we need to show this. So if we, so this kind of arrangement here, this drawings here represent the mechanism of this reaction. And you see now this bromine ion, now the bromide, if we look at the equation, this bromide ion now will join, if the hydroxide was coming out of sodium hydroxide, for example, like as we have here, remember this is, we can see it, the sodium hydroxide, we can see it as a positive ion and the negative ion, the hydroxide. Now this bromide ion will join with this sodium ion, and the result will be the sodium bromide, the formation of sodium bromide, whereas the rest, what formed out of the bond between the hydroxide and this carbon is now this product here, which is now an alcohol. It's an ethanol. And this is how the mechanism of this type of reaction takes place. So you see, for us to show the mechanism, there was no need to show, for example, what happened to the sodium ions. We just concentrated on this hydroxide that replaced the bromine atom from the bromoethane. All right. If the same thing could happen instead of if instead of the hydroxide ion we had the cyanide ion, again the same thing, but remember we must also show the lone pair of electrons in this ion. And by the way, if we to understand for us to understand what is this pair of electrons, where does it come from, and if we draw somewhere here the electronic configuration of the hydroxide ion, we would have the oxygen linked to a hydrogen, but also its remaining electrons in the outer energy shell of the oxygen. The oxygen usually, let us see the periodic table. Where is the periodic table? How many? Here it is. Here is the oxygen in group 16, or the old group 6. It means it has 6 outer electrons, and a neutral atom of oxygen has 6 outer electrons. And here, in our case, where we have Okay, 1, 2, 3, and 4, 5. 4, 5, and 2, 4, 6, and these electrons, this pair of electrons belong to hydrogen and oxygen together. Now the oxygen has 6 electrons, outer electrons, isn't it? 2, 4, 6, but there we can see that it has an extra electron here, and that is the reason why it is now a negative ion. This extra electron is here that participates in this bond between the hydrogen. Okay, so this kind of electronic configuration represents the electronic configuration of this ion, the hydroxide. And because it has an extra electron, that is why altogether it's negative. And now let us see an example where we have the ammonia, which is not a negative nucleophile. It is a neutral nucleophile. Now it's a molecule. Ammonia is a molecule, isn't it? So now let us see this ammonia case, where we have again bromoethane, which is again a saturated heterocarbon. And now it reacts with ammonia, and these are the two products. Now let us see the mechanism here. So let us write again this bromoethane in this form. And here's the bromine. These are hydrogens. All right. And this now will react with ammonia. Now the ammonia, how can we represent the ammonia to understand the mechanism of this reaction? We need to show the lone pair of electrons on the nitrogen and of course the 3 hydrogens. So this is how we can represent the ammonia in these cases, just to show, for us to show the lone pair of electrons. Okay. So once again, if we go up to this compound, this is a polar molecule again, because the bromine, due to the difference in electronegativity as before, the bromine is more electronegative atom, so therefore it has a negative partial charge, and this carbon here, which is attached to the bromine, has a relative positive, a partial positive charge. So there we see the dipole here. So obviously the ammonia, in fact this pair of electrons, which is a nucleophilic center, will be attracted to this carbon. And how do we show it? With a curly arrow, we can show that this pair of electrons will join with the carbon here. And at the same time, of course, the pair of electrons of this bond, this covalent bond between carbon and a bromine atom, at the same time will break, and both the electrons of this bond will go to the bromine. And let us write here what will be the product that we'll have out of that, out of this process. Here, instead of bromine, now we'll have this ammonia lot, ammonia with 3 hydrogens, and the other hydrogens in the carbons stay where they were. Okay, and now, and of course, the bromine took both the electrons, this pair from this bond, and therefore it's here. It is a pair of electrons, and it's an ion, a bromide ion. Now, the important aspect here, this is an intermediate product, and this tends to be positive. This nitrogen tends to have a positive charge. Why? Because one of its electrons actually shared with this carbon, and it is, in effect, this means it's like effectively it's down by 1 electron. That is why it appears to be to have a positive charge. So this is kind of a positively charged byproduct, intermediate product. And so we're not finished here. So now what happens now? because of this positive charge now, this pair of electrons will move to this nitrogen, and this hydrogen now that will end up positive will react with another ammonia. You see this ammonia molecule that reacted initially with this bromoethane. Now another ammonia molecule, let's write it again here, another ammonia molecule now will react with this hydrogen, which has become positive now, and which means this pair of electrons will be shared with this hydrogen. And what we're going to have, let me see if I hope I have enough space to write here. Now things change here. What happens now is that this hydrogen left and reacted with this ammonia molecule. And what do we have here left? We have a nitrogen that is left with two hydrogens now because the one is gone. And of course, these are the hydrogens here. So we have one of this is the new product, and plus this hydrogen that joined this ammonia. And what does it make? One extra hydrogen in this ammonia makes an ammonium ion, which is a positive ion, as we know. And of course, remember that we also have this bromide ion that was left from this stage here, isn't it? Plus this bromine ion with its pair of electrons. And finally, these two, in other words, these two now can combine because the positive and the negative ion attract one another. And these two combined together produce an ammonium bromide. And there is this product that we see here in the equation, the initial equation. Whereas this product here, it's actually what was formed in this last stage. And how do we call this? This is an ethylamine. Ethylamine. Sorry, not amine. Amine, actually. Ethylamine. Ethylamine. I have it correctly spelled. Ethylamine. Ethylamine. So this is that is why the product between of this reaction between a bromoethane and ammonia produces ethylamine and ammonium bromide. And we see that we needed two molecules of ammonia. The one molecule was involved in this first step to produce this first byproduct, and then the second ammonia molecule joined with this hydrogen that was removed from this byproduct here, this intermediate product, and produced and left the ethylamine, and this hydrogen joined with the ammonia and produced this ammonium ion, which joined with a bromide ion and formed the ammonium bromide. All right. Now, let us stop here. And do you understand here this mechanism, how it worked out, especially this part with the ammonia, the substitution that involved the ammonia molecule? Good. All right. So here, that is a very interesting phenomenon that we saw. The ammonia molecule in each case in these two steps played a different role, if you noticed. I mean, in the first step, it behaved like the nucleophile that donates a pair of electrons. So that was, here it played the role of the nucleophile, which donate a pair of electrons to this carbon. But here, this ammonia played the role of a base. a base that reacted with hydrogen. So here actually a Bronsted Lowry base. I don't know if you remember your bases, Bronsted Lowry base. So we have this ammonia molecule reacting in two ways. One as a nucleophile and another as a base. Nevertheless, I mean, you don't have to know that, but it's interesting to know to see the different roles that this ammonia molecule plays. And also that is why we had two there. I mean, we did not place a two because we had two ammonia molecules. I mean, obviously, this reaction is balances the reaction. And we would expect these two to appear there because this ammonia is not the same molecule as this one. It's a different molecule of ammonia. All right. And so now let us go to these initial reactions. So we saw this type of, the mechanism of this reaction where we have the organic compound to react with a negatively charged nucleophile, like the hydroxide in this case. We also saw, no, it's not here. We saw also the reaction when an organic compound reacts with a neutral nucleophile, and this is a nucleophile just because the nitrogen has a lone pair of electrons, yeah? The hydrogens. So it is a neutral nucleophile, but it is a nucleophile because of this lone pair of electrons. And let us see now the mechanism where we have the formation of free radicals, which react and with our organic compound. This and this actually would be exactly the same case as the first case with a negatively charged nucleophile, okay, because we would have a negatively charged bromine ion and okay, there's no need to waste time. So now let us go. Let us look now at this reaction here where we have the formation of free radicals, which is actually the reaction that is, it appears in your book actually, where is that, on page 206, 207. They don't have the ethane, they have methane, fine. Let us look at the methane. Reaction of methane with chlorine. Okay. Let us write the reaction generally. We have methane with chlorine gas, reacts and gives us a chloromethane plus hydrogen chloride. But for this reaction to happen, we need to have sunlight. Otherwise it cannot happen. This reaction cannot happen without light. And in fact, we need the UV part of the light that falls. And why do we need the light in this case? Is because in order for this molecule to break into two parts, which we call free radicals. So let's start now in order. So the first step is initiation step. It has a name. The first step, which we call the initiation step, is to break a chlorine atom. And this can only break if we have light here, sunlight. In fact, we need the UV light. All right. So what happens now? The light might break one of these molecules, and what we'll have now, we'll have two chlorine atoms, and each of these chlorine atoms picks up one electron from the bond between the two chlorine atoms in the chlorine molecule. So each of these chlorine atoms ends up with one electron from this bond. And in fact, this type of breaking down of a molecule is called the homolytic fission. Homolytic fission. Fission means means the splitting of something. Usually they use the expression to the splitting of the cells in biology, but it has been borrowed from other processes where we have splitting, as in this case, where the chlorine molecule splits into two parts, but in these two parts, each one picks up one of the electrons, so they are kind of asymmetric splitting, asymmetric fission. So that is why it's called homolytic fission. Now, these two items that we are left with are called free radicals. Free radicals, and free radicals are very, very active and attack other species. And so they're very reactive. So these two are free radicals now. Now, in the next step now, one of those free radicals perhaps will collide with one molecule of methane. So what we'll have here, and this free radical, it will react with it. In fact, we'll say it attacks the molecule of methane because it's so active. So it attacks it, and what happens is that it produces, removes one of the hydrogens. In fact, it's better if we show it in this form, as always, with a free radical here, attacks it breaks the bond between this covalent bond between the carbon and the hydrogen, and the hydrogen comes out with picking up this electron, and it becomes like a radical itself. Do I have this? Yeah. Where would we? Yeah. Okay. Now this one, this item here, this is also a free radical. It's also a free radical, and it is called a methyl free radical. And because it is a free radical, it's again very active. Where am I? Sorry, what was I saying here? Yeah. Do I have this all together? Yeah. I'm making too much, a lot of a mess here, sorry. Oh dear, 12 o'clock. Okay, maybe that's better. Maybe we can start it from the beginning next week, because I think I've made a mess here with all my, I don't know where I am anymore. Okay, guys, we'll continue this with the free radical substitution next week. We'll start it from the beginning, all right? So, goodness, 12 o'clock. All right, guys. So, stop sharing now. We'll start it again from scratch. All right. So, I might see you tomorrow, okay? Bye.